Hello, this is the fourth video of the Preliminaries 2 series on further sets, combinations and permutations for OCR Discrete Further Mathematics, and the title is Derangements. A typical derangement problem involves a rearrangement in which none of the objects keeps its original place. For small numbers of items, it's best to use reasoning, so let's start with just two objects. Say A and B. Well, we could rearrange these as BA, and of those two options, only one is valid because in this option here, we have the original positions. So therefore, the only derangement is BA. Using the notation for derangements, D of n, we can therefore see that D of 2 equals 1. For three objects, we already know that there are 3 factorial or 6 arrangements. Let's use the letters A, B and C, using those as the original positions. Now we could list all the 6 arrangements of ABC to see which are derangements. So we could have ABC or ACB. We could have BAC or BCA. Or we could have CAB or CBA. Let's rule out the ones in which we have either A, B or C in their original position. So clearly those two, we have A in the original position. So that's no good. In this one here, we have C in the original position. So again, that will not work. In this one here, we have B in its original position. So again, that is not a derangement, leaving us with just 2 derangements. Therefore, we can say that D of 3 equals 2. For 4 objects, we would have 4 factorial or 24 arrangements, and we could again list these to see which are derangements, but it's helpful to think about this more theoretically. So using the letters A, B, C, D, with A, B, C, D being the original position, we know that there are 3 ways to fill the first position, which are derangements. In other words, you can't choose A because that would be in its original position, but we could choose B, C or D. Let's look at the case where we put B in that first position. Subsequent to that, we have 2 cases. Either case 1, where A swaps with the letter that replaces it, so we would have BA. And then we have 2 slots left for C and D. They must not be in their original position, so in other words, C cannot go in the 3rd slot, nor D in the 4th, and that leaves us then with the option of D and then C. The case 2, where A does not swap with the letter that replaced it, in this example we've gone for B, being the letter that replaced it, then that means that A cannot go into slot 2, because we've already dealt with that in case 1. That C cannot go into slot 3, because that would be in its original position, so it wouldn't be a derangement, and D cannot go into slot 4. So we have 3 slots, 3 letters, but actually a limited number of options. We could put D in slot 2, A in slot 3 and C in slot 4. Or we could also put C in slot 2, D in slot 3 and A. So bearing in mind that that first letter could have been filled in 3 ways, in other words B, C or D, and that we then have one option in case 1 and 2 options in case 2 gives us that D4 equals 3 times D2, which was this one here, plus D3, which was that one there, giving us a total of 9. The method we used for finding D4, in other words the number of derangements for 4 objects, can be extended to cover larger examples. Let's consider 5 objects, which we will label A, B, C, D and E. So once again, there are 4 ways of filling the first slot, given that we can't use A because that's its original position. So we have 4 choices left. And then we have the 2 cases, either where A swaps with B in effect, or the second case where A does not go into that second slot, replacing B. We would find that that would give us D3 ways, and that this would give us D4 ways. Remembering there was 4 ways of choosing that first slot. Hence, for 5 objects, the number of derangements, or D5, will therefore equal that 4 times D3 plus D4, which equals 4 times 2, because we already know that D3 equals 2, plus 9, which we already know is D4, giving us a total of 44. And in general, we'll find that D to the n equals n minus 1 multiplied by D of n minus 2 plus D of n minus 1. There is no need to memorize this, but it is important to understand where this recurrence relationship comes from. And we can see that the number of derangements builds quite rapidly. So for example, D of 2 equaled 1, D of 3 equaled 2, D of 4 equaled 9, but D of 5 is 44. In this example, 6 people go to a party and each of them leaves an umbrella by the entrance. When the party ends, each person takes another person's umbrella, probably by mistake, obviously a good party. So in how many ways might this be possible? If we use the recurrence relationship that we've already identified, we know that there are 6 people, so we are looking for D of 6. And this will equal n minus 1, or 5, lots of D to the n minus 2, or D of 4, plus D of n minus 1, or D of 5. We already know that D of 4 equaled 9, and that D of 5 equals 44. And this gives us 265 ways. As you can see, the recurrence relationship is very easy to use, and we can also see that the number of derangements is indeed increasing very rapidly as the number of objects increases. This is the last video of the Preliminaries 2 series.